everyone, welcome to the course on electromagnetic theory and interference. In this last session, we will see about the wave propagation in the waveguide, rectangular waveguide. So see, as we can see, this is the point where the waves are injected. We can see the wave is getting reflected from the walls and it is flowing in a zigzag manner along the direction of wave propagation. So the wave component in the Z direction, it is having the different wavelength compared from the plane waves. So that particular wavelength along the axis of the guide is called waveguide wavelength, which is represented by lambda. That is equal to lambda dash divided by the factor that we will usually take, 1 minus root of 1 minus fc by f the whole square. So we already know lambda dash is u dash by f, velocity by frequency. So because of the zigzag path, we have three different velocities. That is, along the wave path, we have medium velocity u dash, and we have phase velocity and group velocity. Okay. So the relation between three velocities are depicted here. The medium velocity, we know it is u dash, that is equal to 1 by root of mu epsilon. Phase velocity is nothing but the velocity at which the locus of constant phase are propagated. Okay. The constant phase, its locus, how it is propagating down the gale is known as phase velocity, and that is equal to omega by beta. The phase velocity, as we can see from this relation, it is equal to the medium velocity and divided by angle of the wave at which it is touching the walls of the waveguide. So if you we can see it is equal to the velocity u dash, plane wave velocity of plane wave, divided by the same factor 1 minus fc by f the whole square. So here the interesting fact is that the phase velocity is greater than or equal to the medium velocity. Why? Because cosine of the angle, maximum angle is 1 only, or it can be less than that. Okay, the maximum angle of force is less than or equal to 1. So in that case, okay, if you consider medium velocity as free space and it is equal to the speed of light, the phase velocity is greater than the speed of light. So we have to check whether it is violating the Einstein theory of relativity. So here messages cannot travel faster than speed of light because the information in the waveguide generally does not travel with the phase velocity. It is going to travel with the group velocity, and which is going to be less than the speed of light. So group velocity Ug is nothing but the velocity with which the resultant reflected waves, okay, resultant reflected waves, how they are traveling down the guide. This is a resultant reflected waves, right? How they are traveling down the line is called the group velocity. So Ug is nothing but 1 divided by d beta by d omega. So if you find Ug, it is u dash multiplied by cosine of the angle. So the wave velocity is multiplied, the medium velocity is multiplied by the same factor. So if we multiply phase velocity and group velocity, it is equal to medium velocity square. So let us see one problem. Here the standard air-filled rectangular waveguide with the dimension is given, and it is fed by a 4 GHz carrier signal from the coaxial cable. We have to find whether T10 mode will get propagated inside the waveguide, and if so, we have to find the phase velocity and group velocity. So let us check whether this waveguide supports T10 mode. For T10 mode, we know cutoff frequency is u dash by 2a, and since it's air-filled, we have to replace by velocity of light, and so 3 to 10 power 8 divided by twice the dimension we are going to take, okay, and convert this dimension in centimeter to meters. We get the frequency. So the cutoff frequency is, we can see whatever the frequency is injected inside the waveguide is more than the cutoff. So T10 mode will be obviously getting propagated. and the phase velocity, we know that it is equal to u dash divided by root of this factor, and u dash is the air here. So we are substituting the value of u dash, which is equal to the speed of light, and 1 minus the cutoff frequency that we found, and we have to divide it by the frequency at which the signal is rejected in the waveguide, that is 4 gigahertz, and we get the phase velocity. Phase velocity will be always greater than the velocity of light. Okay. When we go for group velocity, we are not taking the first formula, that is u dash into root of 1 minus xc by f the whole square. We know this relation, right? That is u dash square by up. The product of phase and group velocity is equal to the medium velocity square. From that, the medium is air, so we are taking the speed of light and dividing by the phase velocity that we have already computed in the previous step. And we can observe that group velocity is less than the speed of light. I hope you understood how the wave is getting propagated inside the guide with a different wavelength called waveguide wavelength, and it is experiencing three types of velocities: medium velocity, phase, and group velocity, and how they are interrelated, and we solve the problem based on this. And this ends the module 3, okay, of electromagnetic waves and waveguides. We will meet you in the next module, transmission lines. Thank you, everyone.